Namaskaram. In this session, we will discuss more properties of permutations in SN. Bubble sort algorithm is a simple algorithm for sorting a given n set of numbers in ascending or descending order. Here we consider the ascending order. For example, consider a sequence of numbers 6, 3, 1, 5, 4, 2. We have to rearrange, we have to sort this number in ascending order like this 1, 2, 3, 4, 5, 6. The algorithm of bubble sort is very simple. Each time you encounter a neighboring pair such that ai is greater than ai plus 1, then just interchange the pair and go back to the beginning and do the same process. Now we will see the relation between permutations and this bubble sort algorithm. Okay, in this example, we have to find the ascending order sequence corresponding to this given sequence. Okay, using bubble sort algorithm. So the first pair is 6, 3. It is clear that this is not in ascending order. So we have to change these two positions, 1, 2, right? So what happened? This is 3, 6, 1, 5, etc. Again, we have to start the same process from first position. So think about the first two. The first two is already in ascending order, so there is no change. Then what about the second and third position? This is not in ascending order, so we have to change 2 and 3. Okay, so this become 3, 1, 6, 5, 4, 2. Then again we start from the first. So what about 3, 1? This is not in ascending order, so we have to change first and second position, right? Similarly, you can continue. So after 6 operation, we have the required ascending order sequence. So this is our bubble sort algorithm. So we can say that the process of switching neighbors corresponds to the symbol transpositions. For example, in the first case we use the transposition 1, 2, right? In second case this is 2, 3 and this is 1, 2. All are symbol. So altogether we have 10 transpositions. So 1, 2, 2, 3, 1, 2, 3, 4, etc. The last one is 2, 3. So these numbers refer to the positions in the sequence, right? Next, we are going to represent the first step in the bubble sort algorithm in terms of permutations in S6. Okay. So what about this first given sequence? Given sequence can be represented using a permutation like this, because in first position it is 6, in second position it is 3, right? And third position it is 1. So we can represent this sequence using a permutation in S6. And you think about the composition of this permutation and the cycle 1, 2. Both are belongs to S6. So it is clear that its composition is this one. And what about this 3, 6, 1, 5, 4, 2? This is the second entry in the bubble sort algorithm. Okay, similarly, what about the last sequence? So this is nothing. This is the identity map in S6, right? So using composition of permutations, we can find this identity. That means if we denote this permutation as sigma, then it is clear that sigma dot these cycles gives exactly the identity. That is, this composition, this 10 symbol transpositions equal to identity map. And we know that the inverse of transposition is itself. So you just cross multiply both sides using these transpositions in this order. That means 2, 3, then next one 3, 4, then 4, 5, etc. Last one is 1, 2. Then it is clear that this become I. Then similarly these two pairs are I. Ultimately this side is I, sigma into I. So left hand side become our original permutation sigma. And what about the right hand side? Right hand side is I into these permutations. That is exactly the permutations 2, 3, 3, 4, etc. up to 2, 1. So this example shows that every permutation can be represented in terms of symbol transpositions. So there is a natural question. What is the minimum number of transpositions needed for writing like this? For addressing this problem, we have another definition that is called inversion. Let sigma belongs to Sn be a permutation, a pair of indices ij where I should be less than j. Okay, is called an inversion of sigma if sigma I is greater than sigma j. Okay, that is called inversion. And collection of all such inversions is denoted by I sigma. And number of inversions is defined as n sigma. So n sigma is equal to the size of I sigma. I sigma contains all the inversions corresponding to sigma. For example, you consider the permutation 1 goes to 2, 2 goes to 3 and 3 goes to 1. What are the inversions? It is clear that the maximum number of inversions in this example is only 3, because the first condition is I should be less than j. It is clear that we have only 3 options. 1 is less than 2, 1 is less than 3 and 2 is less than 3. Next you have to check whether which are the inversions. Consider first one. Here I equal to 1 and j equal to 2. So what about sigma 1? Sigma 1 is 2. What is sigma 2? That is 3. So it is clear that 2 is less than 3. So this is not an inversion. This is inversion only when sigma I is greater than sigma j. What about the pair 1, 3? 1 goes to 2, so sigma 1 is 2, and 3 goes to 1, so sigma 3 equal to 1. So it is clear that 2 greater than 1. Yes. So this is an inversion. Similarly, this is also inversion. 2 maps to 3 and 3 maps to 1, so 3 greater than 1. So for this permutation, we have only 2 inversions. The pair 1, 3 and 2, 3. Right. We will see in later that the minimum number of symbol transpositions needed is exactly n sigma. Similarly, you can find all the inversions of this permutation and number of inversions equal to 10. For example, 1, 2 is an inversion that belongs to I sigma, but 3, 5. 3, 5 is not an inversion, that is not belongs to I sigma. Anyway, altogether there are only 10 inversions. Okay, next proposition. The permutation sigma belongs to Sn is the identity map if and only if n sigma equal to 0. Similarly, if sigma is not the identity map, then there exists at least one I from 1 to etc n minus 1 such that sigma I is greater than sigma I plus 1. Okay, in this example it is clear that, but what about these two pairs? Sigma 4 is greater than sigma 5 because sigma 4 is 6 and sigma 5 is 4. So the theorem says that at least one I such that sigma I is greater than sigma I plus 1. So suppose sigma is an identity map. Then we know that it has no inversion. Why? Inversion means if I less than j, then sigma I is greater than sigma j. So in the case of identity map, we know that suppose I is less than j, then sigma I equal to I, sigma j also j. So still sigma I less than sigma j. This is not greater than. Okay. So it is clear that if sigma is an identity map, there is no inversion. Conversely, suppose n sigma equal to 0. Then we have to show that sigma is an identity map. Suppose sigma is not identity map. Okay, since sigma is not identity map, there exists I belongs to Mn such that sigma I not equal to I. We consider smallest such I. Then our claim is sigma I is greater than I. Then why? Because we consider this example, suppose 1 maps to 1, 2 maps to 2. Suppose sigma 3 is not equal to 3. So this is the first such I. Okay, this is the first such I. Okay, then it is clear that we cannot map sigma 3 to any of the numbers which is less than 3. Why? Because we know that sigma is a bijection. So we can map sigma 3 to a number which is greater than 3 because we already used 1 and 2. So if sigma is not an identity map, there exists a smallest I such that sigma I is greater than I. So in this example, the such I is equal to 3, right? So of course this 3 is image of some number which is greater than 3. That means 3 is somewhere here. So what about the inverse of this 3? 3 or I. So inverse of 3 which is greater than 3. So you can conclude that sigma inverse of I is greater than I, right? Or we can say that I is less than sigma inverse of I. Then we consider the sigma on both sides. So left side becomes sigma of I and right side it become I. So what is the relation between sigma I and I? See, already we choose I such a way that sigma I is greater than I. So what is our conclusion? The pair I comma sigma inverse of I is an inversion. This is a contradiction to our assumption that n sigma equal to 0. So sigma must be identity map. Okay, in the second part, we have to show that there exists a I such that sigma I is greater than sigma I plus 1. Suppose this is not true. That means sigma I is less than or equal to sigma I plus 1 for all I. Okay, since sigma is a bijection, equal to is not possible. That means sigma I is less than sigma I plus 1 for all I is equal to 1 to n. That means sigma 1 is less than sigma 2 is less than sigma 3, etc. less than sigma n. This means this sigma has no inversion, because it is clear that if I is less than j, then sigma I is also less than sigma j. That means there is no inversion in this sigma. That means n sigma equal to 0. In our previous already shown that if n sigma equal to 0, then sigma is an identity map. But in second part, we assume that sigma is not an identity map. So that is a contradiction. That means this assumption is wrong. That means there is at least one I such that sigma I is greater than sigma I plus 1.